Good day. For those of you who don't know me, my name is Douglas Harder. In this topic, we're going to look at finding numerical approximations to solutions to the wave equation. So in this topic, we're going to review the physical problem and its properties. We're going to look at the equation itself, and we will see how we can approximate it using a finite difference equation. We will then look at an implementation of this approximation. We will consider numerical stability. We'll see a few examples, and then we will see how we can apply some of these ideas to the Crank-Nicolson method and vice versa. So by the end of this lab, you will understand the wave equation. You will understand how to approximate the partial differential equation using finite difference equations. We will set up solutions in one spatial dimension. Again, that would be one spatial dimension and one time dimension. And we will deal with insulated boundary conditions. So suppose we have a string at rest. Someone comes along and decides to pluck that string. Now what happens? The string begins to vibrate. Now, energy is, of course, however, being transferred to the air, and this produces sound. As well, there's internal friction, which is causing heat. And so over time, the string will dampen until it stops vibrating altogether. We're going to deal with a case where there are no frictions and no energy being transferred out of the system. So note that if a string is at rest, it's not moving. It's a solution to Laplace's equation. However, if it is moving, there seems to be acceleration towards the solution to Laplace's equation. So now at the bottom, initially it seems to be quite slow, but then it speeds up. As it moves away from Laplace's equation, it slows down until it begins speeding up back towards the solution. Now, what happens if we reduce the length of the string? At least if it is an actual physical string. It's moving up and down, but let's say we cut the length of the string in half. In this case, we notice that the frequency doubles. It seems to be moving significantly faster. This is very important in music because, in this case, if we consider a certain string and it happens to be playing, say, middle C, well, if we cut the length of the string in half, then it will play a C one octave higher. If we cut the length of the string again in half, it will have a frequency equal to C one octave yet higher. At the same time, if we double the length of the string, then we go down one octave. Now, waves are not restricted to strings. We of course see waves in two dimensions on the face of a drum. The ripples on the surface of a pond are again another two-dimensional example of waves. You, as electrical, computer, or nanotechnology engineers, will be interested with respect to the movement of light and the electromagnetic spectrum, microwaves, radio waves, etc. So the equation that describes propagations of these waves under somewhat ideal circumstances is given by the partial differential equation. Second partial with respect to time is equal to c squared, some constant, times the Laplacian of the function. Now here, u is a function both of space and time. And space can be either one-dimensional, two-dimensional, or three-dimensional. In this lab, we're going to consider only one-dimensional problems, but in lab 6, we will see three-dimensional problems. Now, c is the propagation speed of the wave. So for example, sound in air at 20 degrees Celsius moves at approximately 343 meters per second, 1,234.8 kilometers per hour, or about 1 kilometer every 3 seconds. Light, on the other hand, moves approximately 300 million meters per second, or 300,000 kilometers per second. Now, in oceans, however, the speed of a wave is proportional to the square length of the wavelength. So, if the wavelength is 1 meter, then the speed is going to be about 2.5 meters per second. Well, that might be what you see on a beach. On the other hand, if you're talking about a wave created by, say, a tsunami, well, now the wavelength is significantly longer, and therefore the speed is significantly faster. 39 meters per second is approximately 140 kilometers per hour. This is why a wave from a tsunami can cross the Pacific so much faster than, say, a wave on a beach. Now notice that if our function u with respect to both x and t, if it already for some period in time satisfies the Laplacian, well, what that says is that if it is stable, then there is no acceleration. The acceleration is equal to 0. So if we're sitting here and we've satisfied Laplace's equation, then it's not going to be accelerating. Now, if it is not moving, then it will remain fixed. If it is moving, say for example as the spring passes through the solution to Laplace's equation, then it will just continue moving at the same speed without any acceleration or deceleration. So therefore, if in one dimension if the string is already tight and it is not moving, it will not begin vibrating. Now, in one dimension, what does this equation mean? We have the second partial with respect to time is equal to a constant times the second partial with respect to space. Well, essentially, we can think of this visually. Suppose we have a function that is concave up and the function is already moving up. In this case, the acceleration is just going to increase the speed at which it moves up at that one point. Now, if the speed was down, if the string was actually moving down, basically this is essentially saying that at this location it will be decelerating in the downward direction and ultimately will begin accelerating up. Now, on the other hand, if we have a function that's concave down, then the acceleration is also going to be down. If the speed at this point is already negative, if it is already moving down at this point, we will simply accelerate in that direction. If the string was moving at this point in the upwards direction, then the wave equation will be pulling it down until it ultimately starts moving back down towards the solution to Laplace's equation. Now, for a second order ordinary differential equation, we require two integrations to find that solution. With every single integration, we have a coefficient of integration that we have to fix. The way we fix these coefficients of integration can be in one of two ways. We can either specify two initial conditions at some initial time, and again, time variables are usually associated with initial conditions, or we can have a boundary condition. So here we have a second order ODE with respect to space. Since it's second order, we have two boundary conditions at two values a and b. Now, for the wave equation, we actually have two second partials, one in time, one in space, and therefore we're going to require at each space coordinate, so every single point along the string, we will require to know its position. We will also have to know what is the initial velocity. Now, very often we'll have an initial velocity equal to 0, and we'll just see what happens, but there's no reason we could not start with an initial value of velocity or speed that is non-zero. For each point in time, as we progress into the future, we will have to know the boundary conditions at the two endpoints of the spatial interval. So essentially what we're going to be doing is we're actually going to, at least in this example, fix ourselves to an interval of space over an interval of time. Now, how are we going to approximate the wave equation? Well, again, we have two partial derivatives. We have two second-order centered finite difference, divided difference approximations of the second derivatives. We can take each of these, substitute them back into the equation. So now we have a finite difference equation that approximates the wave equation. All right, now if we take a look here, here we have t minus delta t, so a point in the past, t, and all of these are t. This is the only term here that is a point in the future. So we know the initial conditions. We want to know what the system is like one step into the future. So if we have all the other current conditions and previous values, then we would like to solve for what the system is like, going to be like in the future. So here we are, we're solving for that point in the future. We have here a ratio. Let's let the ratio be designated by r, and now we get this easier equation, or at least cleaner. Now, as far as we're concerned, we're going to start with an interval AB with respect to space, and we will divide that interval into n sub x equally spaced points where the space between the points is h. Similarly, we will take the time interval and we will break that up into n sub t points, and the difference between those points will be delta t. Now, we will now try to approximate the solution at each of those points. So that gives us a grid, and so at each of these points, x sub I, t sub k, we will approximate it by some unknown value, u sub ik. Now we will have some boundary conditions and some initial conditions, but there's a lot of interior points which are unknown, and we will have to solve for them. Now, x sub I plus or minus h, well, since the x values are separated by h, x plus or minus h is going to essentially be either the previous, or the next, or the previous x value. So it will be x sub I plus or minus 1. Similarly, in time, we will have t sub k plus or minus delta t, and that is either the next t sub k plus 1 or previous t sub k minus 1 points. Hence, we will be approximating this point with u sub x plus or minus 1 t, and here, where we have t sub k plus or minus delta t, well, that is just going to be approximated by the point at t sub k plus or minus 1, and these are approximated by these unknown values, I plus or minus 1k, or I k plus or minus 1. Thus, we've simplified the solution to this equation, which refers to points within a grid. And so now we can associate a point with different values in that grid. The boundary conditions are going to be given by a number of functions. First, we need two initial conditions. The initial conditions are given by u sub init and delta u sub init. This will give us the initial value of the function and the initial rate of change of the function. The boundary conditions, as time progresses, the values of the boundaries might change, and those will be specified by two functions. A sub boundary with respect to t gives us the value of the solution at a for an arbitrary point t. Similarly, b sub boundary gives us the other boundary condition. As with the previous case, as we did with the heat conduction diffusion equation, the boundary conditions will be specified by a single function that returns a vector of values, the first entry being the boundary condition at A, the second being the boundary condition at B. So we have three functions, u sub init, du sub init, giving us the rate of change, and u sub boundary. U sub init and u sub boundary take either a spatial variable or a vector of time points, and du sub init is almost similar to u sub init. It takes an n-dimensional row vector of points, column vector, sorry, and returns an n-dimensional column vector that specifies the initial speed at each of those points. Now, as before, as I've said, we're going to divide the spatial dimension into n sub x points, and of course we will be dividing the time interval t naught to t final into n sub t points. Now recall that in MATLAB indexes start at 1, and therefore our time interval will be broken up into n sub t points going from t naught to tf. However, because the vector is indexed from 1 to n sub t, the first entry will be t naught, so t sub 1, the first entry will be our initial time. T sub out, the last point, will be tf, or t sub final, the last point that we are trying to approximate. Now, here we are, we have the initial values at time t1. How about t sub 2? Well, let's take this equation, let's substitute k is equal to 1, into that equation. So now we have that this point is equal to the previous point with a ratio, with a linear combination of these points, but now we're referring to this point u sub I 0. There's nothing there. We don't have access to that information. We only know the initial state of the system. We do not know what the state was prior to the initial state. Fortunately, however, we know what the initial velocity is, and therefore we can use Euler's approximation. We have the initial state. We know delta t, how far we are going into the future, and we know the rate of change. And so therefore we can multiply the rate of change by delta t and add that onto our initial value. And this is actually good because one step of Euler is order delta t squared. Now multiple steps are not, but one step is order delta t squared. So we still have a big O delta t squared method. Now for the next point, however, t3, notice that all of these values are known. We either previously calculated them or they were the initial values. So from this point on, we can calculate all of the interior points using previously calculated points. And we can do that for every single time step into the future up until the end. All right, so how are we going to solve this problem explicitly? Well, we do have some error checking to do, just like we had with the heat conduction diffusion equation. In this case, we're going to see that this ratio must be less than 1. We'll have some initialization. We have to solve for the special case at time t2. After that, we solve the problem in general. Now, if we have, in addition to this, insulated boundary conditions, we have to break step 4 into 2 steps. First, we have to apply the formula to approximate the interior values, but then we may have to update the endpoints or the boundary points based on the fact that they are insulated. And we'll see that in greater detail. The first step for error checking, however, is we have to make sure that this ratio is less than 0, and we'll see what happens if, or less than 1. And we'll see what happens if that ratio is not less than 1. If this condition is not met, we should exit and a useful error message should be returned. So for example, we should indicate, hey, the ratio is equal to this value, that's greater than 1. Consider using some value of n sub t that is higher, that will not cause this ratio to exceed 1. All right, so why would we suggest a different n sub t value instead of a different n sub x value? Well, we are interested in a spatial dimension. What is the, we're more interested in how much do we have to refine the time dimension to get an accurate picture of what's happening. So basically we have to make n sub t sufficiently large. You may want to read up on the floor and the ceiling functions again before you look at this. However, essentially what we're saying is we have these values and we want to find an appropriate value of n sub t star such that that ratio is less than 1. You can find that, you can solve for that, and using the appropriate functions, this is going to be essentially be very similar to the constraints on kappa delta t all over h squared. Now, it would still be useful to initialize the matrix U and then carry on calculating. Now, we've broken up space into n sub x points, time into n sub t points. This suggests, therefore, we should have an n sub x by n sub t matrix of zeros initially. Then we have to initialize it. So here, I would call the initialization function at the x values, which we created with lin space, and copy them into these locations. Similarly, I would call the boundary value function at from t2 to t sub n sub t, and get the a values, copy them here, copy the boundary conditions at x is equal to b, copy them there. We will then proceed to carry on and find the approximations. However, initially we have to use Euler's method with our initial value plus the rate of change at the initial value times delta t. That will give us this first column. Easy enough. Well, actually the second column in the matrix. If these two boundary conditions, or if one of those boundary conditions is an insulated boundary condition, and as you'll recall, an insulated boundary condition is being designated by the boundary condition being not a number, then we have to get a value for that insulated boundary condition because we'll be using it later. So how do we get an approximation? Remember that an insulated boundary condition says that the derivative with respect to space at that time is equal to 0. If you're approaching an insulated wall, you do not expect the temperature to jump up or down the closer and closer you get to the wall. You expect the temperature to essentially remain constant, very close to an insulated wall. So what we did here is we used the second order forward divided difference approximation or backwards divided difference approximation. Having done so, we substituted these two values in, or those two, set it equal to 0, and solve for the remaining unknown. This means that this value here, if it was insulated, should actually be equal to that ratio. Similarly here, this point should be this linear combination of those two values. From here on in, we simply carry on with k is equal to 3, 4, 5, all the way up to n sub t. Again, at each step, you may have insulated boundary conditions. So once you find the interior values, you may have to update the boundary values. So here's an example. Here we have a system where the initial state is sine of t. So the initial state is a string that is in the shape of a sinusoid. Its initial speed is 0, so it's essentially fixed. However, it is under tension, and therefore, when we let go, it will start moving. Both boundary conditions are 0. Basically, we're going to be holding the string tight, and then what happens? Well, as time propagates, this goes down. So here we have pi, the interval from 0 to pi divided into 10 points, the interval from 0 to 10 divided into 42 points, and our initial functions. The output is a vector of x values. It's going to be 10 x values. A column vector of 42, I'll correct that in the slides, a row vector of 42 time intervals, and a matrix that is 10 by 42. I'll correct that mistake. If we call mesh, we get the following output. The initial functions with respect to time is just sine of x. The initial speed is 0, so we'll just multiply the input vector by 0, and that will return a vector of zeros, indicating that the initial speed at each point is 0. And the boundary conditions, we're past a row vector of t values. However, we will return a 2 by n sub t, or actually n sub t minus 2, or minus 1, t values. In this case, all of them will be 0. Also, when you're looking at in MATLAB, you could also select the rotate 3D icon, and that will allow you to rotate the shape, and you can see what's happening as we're propagating to the future. String is essentially vibrating. Now, let's look at slinkies, a trademark name, by the way. But if we start with a slinky and hold the slinky taut and fix both ends, notice what happens. We can give a pulse. Now, how is a pulse defined? Well, in this case, we're going to define a pulse by a cosine function. And now, that wave is going to propagate along the slinky. As we've seen, the wave propagates along, reflects, and then propagates back, and then keeps on reflecting. So again, we start. Oh, we have to go a little bit faster than that. The wave propagates along, it reflects, and then it propagates back, reflecting again. Now in this case, what are the initial conditions? The initial conditions are both 0 for the initial state, and the initial velocities are also 0. What's changing, however, is the boundary values. So this boundary value is always fixed. So the second row is always going to be all zeros. The first row, however, is 1 minus cos of t. Well, 1 minus cos of t is a function that starts at 0, goes up to 2, comes down again, and then keeps on propagating. However, here we're element-wise multiplying it by t less than 2 times pi. So essentially this will cancel out any other wave other than the first one. So up, down, and that's it. So here we are, time t0, we go up, we go down. At time t equals 2 pi, we stop. This boundary condition now becomes fixed. Another possibility, however, is having an insulated boundary condition. So suppose that the other end of the slinky can move freely up and down. What happens then? Well, in that case, the slinky, the wave will move out, it will propagate back without reflection, and now because this endpoint was fixed, we'll have a reflection, it will move out, and then propagate back. So now, the boundary condition at the second point is not a number. Now, how are you actually going to do this with a real slinky? Well, you can actually do it quite easily. What you do is you take a slinky, and you have the one end that you hold that end, where you're introducing the wave, but the other end, take a segment of string about that long, and then tie one end of that string to the slinky. Now the string is almost weightless relative to the metallic slinky, or even plastic slinky, and hold the end of the string. This allows the end of the slinky to move more freely in the vertical direction, but not left and right. So if you try that, you will get exactly this behavior. As you send a pulse out, it will move out, it will reflect back. Because you're holding this end, it will reflect through the x-axis and then propagate out and come back. Finally, let's see what happens if this ratio is greater than 1. Well, it seems to be doing okay. Oh dear, it's starting to... Oh dear. Yes, this is not what you would call numeric stability. If we're playing with a slinky, the slinky is not going to suddenly jump to size 10 to the 6 relative to the size of the actual initial pulse. Now, let's look at a few other ideas. Can we use implicit methods like we did for the wave equation and Crank-Nicolson? Can we implement those here with a wave equation? Similarly, can we use order delta t squared approximations for the derivative in the heat conduction diffusion equation? Because again, remember, there we used only big O of delta t approximations. Well, as far as using an implicit method, I tried it out, tried implementing Crank-Nicolson, and it fails to approximate a wave equation better. In fact, it introduces significantly more error. What's happening here is that it's a question of classification. Second order partial differential equations can be classified as either parabolic, hyperbolic, or elliptical based on the coefficients within the equation. Under certain circumstances, there are different algorithms that we need to use at each step or for each class. And therefore, implicit methods are not as optimal for those within the class of wave equations. On the other hand, notice that when we did Crank-Nicolson and approximated the heat conduction diffusion equation, when we calculated the derivative here, we used a first order approximation. So this was just a first order forward divided difference approximation. Not very, again, now if one component of the equation is big O of delta t, whereas all other components may be big O of delta t squared, we are restricted by the delta t term. So can we use, say, for example, a centered divided difference approximation of the derivative, which is therefore big O of delta t squared? Unfortunately, this doesn't work. This leads to numerical instability. We can, however, use a backwards divided difference approximation of the derivative. In this case, we can actually successfully introduce this into the Crank-Nicolson method, or the more primitive approximation of the heat conduction diffusion equation, which we did in lab 2, and still get a reasonable answer. So this one works quite well. It's essentially the same formula. There's just one extra term here, and we have a few coefficients which differ slightly. You're not going to have to apply this in class, but it's just a few ideas for you to think about. So in summary, we've looked at the physical problem of the wave equation. We've considered how we can implement this in one dimension. We have found a finite difference equation approximating the wave equation, and we can use this finite difference equation to approximate a solution to the wave equation. This ratio has to be less than 1. We looked at the implementation and a few examples, and then we considered insulated boundary conditions. So, good luck on your lab, have a good week, and cheers!